Hey, it's Ryan here with learnometrics.com, and welcome to my course on statics. Up till this point, you've been in general science courses, like you've got your physics classes, your calculus classes, uh, probably chemistry classes, and these are all your general science courses. Now, statics is going to be your first real engineering course. Um, and it's a big step forward, so let's get right into it. I'm going to try to make this course as interesting as I can for you because my statics course was pretty boring in college. The main reason it was boring was because there was very little practical application or creativity required to solve a lot of the problems. For example, here's a problem that you might solve somewhere in the middle of the course. You'd be given the force P right here, and you would be asked to solve for the reaction forces B, O, and D. The problem with these types of problems, or my issue with them, is that you don't need any creativity to solve this. Just apply the formulas correctly, and everybody gets the exact same answer. Whoop-de-doo. It's very easy for grading for large courses, but very, very dull for the student. You are going to have to learn to solve these problems. This is your standard engineering course problems. However, I'm also going to introduce another type of problems. These type of problems, you're going to have to make educated assumptions and defend those assumptions with your reasoning. These are going to be real world scenarios. You're going to have to make assumptions about the weight, about angles, about how forces interact with each other. It's not all going to be given to you. You're going to have to be creative and make real decisions. So, let me give you an example of this type of problem. This would be what you would see on a potential midterm in this course. It's 2007, and you're in the movies watching Fantastic Four: Rise of the Silver Surfer. The London Eye is falling into the River Thames, and the heroes need to save it. Reed Richards jumps up to the center fuselage, right here, and grabs the cabling with his arms. The thing goes down to the base of the London Eye and supports it with his body. And Sue Storm steps out onto the water and uses her force field to hold it up. So she's out somewhere right here. And what my question to you is, what are the force contributions of each superhero to keeping the eye in static equilibrium? Whose is the greatest and why? And then assuming this force is possible for the superhero, this greatest force, what is a potential issue with this scene if it happened in the real world where materials have limits? So this is a more difficult problem because let's look at a few of the assumptions you'd have to make. You'd have to assume what the angle of this Ferris wheel is at. It's difficult to measure. How much does the London Eye weigh? Do you treat it as a point force? Do you treat it as local forces down here? All different decisions you'd have to make. How does Sue's force field exert a power? Is it, or a force? Is it a pressure force? Is it a stingle force? You would have to make these assumptions and make these arguments. So that's an example of what a problem that I would show you how to solve or you would take in the midterm. Let's start with getting into the fundamentals of statics. Statics is based on Newton's 3 laws. The first law can be thought of as the law of inertia. Basically, there is no acceleration without a net force. Said more fancy, an object will not change its motion unless acted upon by a net force or moment. So that means if I have a train moving at a high speed, that train is going to keep going unless there's a friction force on it. It'll start to slow down. Now, what this also means is if that something starts at rest, it'll stay at rest. Or if it starts in motion, it will stay in motion. Think of something traveling through space. There'd be nothing to slow it down. Now, you can have both rotational and linear inertia. This top here is rotating. It has rotational inertia, but it has a small amount of it because it's very easy to stop. You can just grab that with your hand. If you tried to stop this train by plopping yourself down the tracks and pushing on it, that would not go well for you, as we can all observe, because it has a high inertia. So it's hard to change the motion of things with high inertia and easy to change the motion of things with low inertia. Newton's second law is force is equal to mass times acceleration, or the net force on an object is equal to the mass of the object multiplied by its acceleration. And this is your equation you've seen in physics multiple times, F equals ma. Now, this force can be the force coming out of these jet thrusters, so that'd be force of thrust, or it can be the gravitational force causing planets to stay in orbit around the sun. Now, a quick question for you. Is Jupiter accelerating as it orbits the sun? Think about the definition of the first law. The answer is yes, it is, because there's a change in the velocity of Jupiter. Originally, at this point, Jupiter is going to be moving directly up along the path. However, if we go to this point in its orbit, now it'll be moving to the left. This means that because its speed has changed direction, or its velocity has changed direction, there has to have been an acceleration. Finally, we have Newton's third law, which I like to call the 5-star rule. So what this law says is that for every action, there's an equal and opposite reaction. So let's say you're going to give your friend a 5-star because they lost a bet or something. So when your hand contacts the back, this would be called the force of the hand on the back. And you can think of these as long subscripts. That is going to leave a very nice hand welt on your friend's back. However, if you've ever given a 5-star, you also know that your hand is going to sting a bit. And that's because there is an equal and opposite reaction from the person's back onto your hand. So that would be the force of the back on the hand. Anytime two things are in contact with each other, or forces are exerting on each other, there is always an equal and opposite reaction. And the way we would show this with an equation is if we do the sum of forces at the moment your hand is striking the back. Sum of forces equals ma according to the second law. We know that acceleration is going to be 0. So our forces is going to be the force of the hand on the back, I'll just use the shorter subscripts, plus the force of the back on the hand is going to be equal to 0. And if we move them to the other sides, then we have the force of the hand on the back. It's going to be equal to the negative of the force from the back onto the hand. So that's the way to think about these. It's always the force of A onto B for the notation for it. So the second one is always the one that's being acted upon. That's it for this first episode in the statics course. Next up, we'll go over units.